I forgot to do the introduction on the stream, but okay, okay. So just for the sake of the stream, so this will be the last of the new material. This is going to be section 6.4, system of equations in two variables. This is the last of the new material. Our last day of classes is upcoming Wednesday for Morehouse. So then for us, our last day is the Tuesday before that, which is this upcoming Tuesday. The following week, so then we have Thursday and Friday as like a review, but we're not going to meet. And then I'll be in contact as far as the final exam. Okay. And that pertains to all of our students from Morehouse. Okay. So, all right. So let's kind of make our way through this section. So we have a set of equations with common variables. It's called a system of equations. If each equation is linear, then the system it's going to be a system of linear equations or a linear system of equations. If at least one equation is nonlinear, then it's called a nonlinear system of equations. Here's a system of two linear equations and two variables. Every time we have an unknown, we need an equation. So if we're looking at this system, we have two unknowns, x and y, and we have two equations. All right? So every time we have an unknown, we need an equation. A system of equations is sometimes referred to as a set of simultaneous equations. A solution of the system of equations in two variables, x and y, is an ordered pair of numbers a and b such that when x is replaced by a and y is replaced by b, all resulting equations in the system are true. All right. So the solution to a system is going to be any ordered pair that makes all equations true. It's actually this way. Okay, okay. And again, the last day for Pearson should be there next to each assignment. Like, and I think I said it for this upcoming, not this Saturday, but the following Saturday. I usually like the final exam to be the last thing that we do, and we'll do our best to get a sense of where our grades are before we get into the final. We want to verify that the order pair 3, 1 is the solution of the system, right? Go ahead.
You was breaking up. You said not this Saturday, but you said next Saturday.
I think it's next Saturday. It should be there with each assignment. I would anticipate next Saturday, but the due date should be there. And again, idealistically, we want the final exam to be the last thing that we do. Okay. I might extend. Ooh, my connection isn't. It's nothing I can do. Like, there's nothing I can do to make that better. Yeah. Okay. So let's see. So we want to verify that the order pair 3, 1 is the solution to the system, right? So all we're going to do is plug in when x is 3 and when y is 1. All right. So we're going to get 2 times 3 minus 1. That's going to be equal to what? 6 minus 1, which equals 5. So that one checks out. Then we have 3 plus 2 times 1 equals 3 plus 2 equals 5. That one too checks out, right? So then so we've confirmed that the order pair 3, 1 is the solution to the system. And here's a type version of what we just did. Okay. So then we're actually use the graphical method to solve the system of equations. Okay, let's introduce some graph paper like this. Boom. All right. I think that's okay. Let's see. So I'm going to do. Let's see. So first, if I think of what method, we'll find the intercepts. We'll use the intercepts this time. So let's see. So this will be the positive x direction. This will be our positive x. Our positive y will go like this. Okay. Let's move this like this. That looks better. One more. Maybe back one. Okay. And again, this is our positive y. Let me see. So for equation 1, when y is 0, x is what? 2? So it looks like for equation 1, the x-intercept is 2, 0. I'm just trying to get a sense of my numbers. And then when x is 0, y is negative 4. Okay, that's equation 1. And then equation 2, when x is 0, y is, what is that, 4? And then when y is 0, x is 6. Okay. So it seems like if I go maybe 7 or 8 in all directions, I think we'll be good. Okay. So then we're just going to make some tick marks. Let's see. 1, 2, 3, 4, 5, 6, 7. We really need one more. I'm going to go 8. Let's copy, paste. Let me get rid of this. Let's paste. Let's rotate. I'll do with this in just a moment. Okay, I think we can extend the y-axis some. Let's just paste again and rotate. Okay, looks decent. Let me see who this is. Okay. He's in there. Okay, and let's go ahead and label our axes. So label our tick mark against the origin. We have 1, 2, 3, 4, 5, 6, 7, and this is 8. Let me move this over some. This is 8 here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. And these are negatives. And then what I'm going to do is I'm going to use this for future. So I'm going to make a copy of this. Let's copy, paste. Okay, we're going to use this one. All right. Let me kind of move these guys out of the way a little bit. Okay. So let's graph the first one in blue. Let's do this one in blue. And then let's copy and paste. Oh, paste. And we'll do this one. We'll do this one in red. Fill with red. Okay. Okay. So if we're doing equation 1, we have what? The x-intercept was 2, 0. The y-intercept was 0, negative 4. Then we connect it with a straight edge. Let me see. 4 divided by 2 is 2. Let me see. 2 over 1. Oh, and let's do this. Paper. I mean, we really just need a straight edge. Connecting like this. And let me just move it around. Okay, that's what I'm looking for. And then we're just going to put arrows on it. All right, so that's equation 1. Let's see, that looks good. And then equation 2, here, let's do like this. So now that's there. And then this one, let me see, I just want this, that, these guys. And then let's go style. I think I got the right stuff. Okay. So we're going to do that one in red. What is that? The y-intercept is 4. The x-intercept is 6. And we just connect it with a straight edge. What I'm going to do is go like this. Just kind of get close. And then just move it around until it fits properly. think it's that one. Not that one. That one's close. That one's on. Okay, I think that's it. Nope. Nope. Sorry, I'm just being a little meticulous. That looks okay. That's close enough. I'm just kind of eyeballing. All right. Okay. So now we actually solved this one graphically. Let me check the times. That took way longer than I wanted it to. Forgot this class. We don't have a lot of time, so I'm going to go a little bit faster. Okay. So we want to solve this graphically. It looks like it crosses. I think it's like 3-2. I think it's supposed to cross at 3-2. I didn't do it the same way I normally do it, but I think it's still kind of there. This one. I think it's 3-2. I think it's supposed to be 3-2. I didn't draw it all the way proper. Let me see, but we can test 3-2, right? So let's see if 3-2 works. So then we're gonna check. And let's thicken this up a little bit. So let's do a check. Okay, so then if we say 2 times 3 minus 2, that's gonna be what? 6 minus 2 equals 4. So that one checks out. And then 2 times 3 plus 3 times 2 is going to be what? 6 plus 6, which equals 12. And that one checks out as well, right? So 3, 2 is a solution to the system. So in a graphical sense, where the lines or where the equations cross, that's going to be our solution set. And again, I didn't draw it all the way proper. I think it's this guy's off. I think this is the one that's off. I need to be like here. One of these guys. What's the slope here? The slope is, right, so then 4 over 6, 2/3, a negative 2/3. So if I go down 2 and write 3, 1, 2, 3, it needs to be there. Okay, that'll do. I'm just being ridiculous. Anyway, I'm nitpicky. Anyway, the idea is there, right? Crosses at 3, 2. Okay, let's go on to the next one. So I think, okay, so they did the same thing. They graphed the intercepts. We got a colors bracket, but that's fine. And I think 3-2 is the same thing. So solutions of a system of equations. So say we have a system of equations, and a solution set of a system of 2 linear equations and 2 variables can be classified in one of the following ways. Either there's one solution where the graphs cross at one point. The graphs can be parallel and they never cross, so there would be no solution. Or one graph could be a multiple of another, so the 2 graphs are on top of each other, so then there's infinitely many solutions. All right, so those are the 3 cases. So we're asked to solve this. So we're asked to solve this with the substitution method. It looks like we need some space. I'm gonna add a page and get a copy of this. Okay. I think this space might be okay. All right. And let's do it like this. Paper, graphic. Okay. So we're asked to solve the system by substitution, right? So what we're going to do with the substitution method, we're going to solve for one variable from one equation and then plug that result into the other equation. So to me, it looks like it's easiest in equation 2 to solve for y. So if we add 2x to both sides, we get y equals 2x plus 9, right? Then we take this and plug it into equation 1, and we'll get 2x minus 5y equals 3. But again, y is going to be 2x plus 9. So notice at this stage, we have one equation, one unknown, so now we can solve, right? So then we can distribute, and we'll get this. going to be minus 10x minus 45 equals 3. Looks like it's going to be negative 8x equals 48. So then x equals 6. X equals negative 6. Okay. Oh, that's just x, right? So we're not done. So if that's x, then we need to go back and find y. So then y is going to be equal to 2x plus 9. That's going to be what? Negative 12 plus 9, which is negative 3. So then our claim is that the solution is going to, the ordered pair is going to be negative 6 comma negative 3. Again, this was a demo on the substitution method. Solve for one variable from one equation, and then plug it into the other equation to get the second variable, and then we get an ordered pair. Then we just need to check. So if we check, we're going to have 2 times negative 6 minus 5 times negative 3. That's going to be what? Negative 12 plus 15, which is going to be 3, and that checks out. Then we're going to say negative 3 minus 2 times negative 6. That's going to be negative 3 plus 12, which is 9, and that one checks out as well. Okay. Okay, paper. Let's go like this. So I think this is just going to be a type version of what we just did with like some explanation, right? I think they get the same result that we got. Negative 6 comma negative 3. Solve the system. Okay. So we can use the same method. Let's solve for y from the first equation. So then we get y equals negative x plus 3. Okay. So then we can take this and plug it into the second equation. We get 2x plus 2 times y equals 9, but y in this case is negative x plus 3. Let me do this just so it can kind of pop a little bit. Okay. So then if we distribute, we'll get 2x minus 2x plus 6 equals 9. These add to 0. We get 0 equals 3, which is false. This is false. So notice that the variables canceled here, and we finished with a false statement. So then this is an example of a contradiction. So that means there's no real number is going to work. So we said the solution set is the empty set. This is a 0 with a slash through it. It means null set, empty set, or no solution. Right? So there's nothing that's going to work. Again, our variables cancel, and we finish with the false statement. This is an example of a contradiction. Here's a type version of what we did. And so if we were to graph both of those lines, we would see that they're parallel lines, and they'll never cross, so there won't be any solution. Okay, let's give this one a go. So we can use a similar method. I think solving for y in the second equation might be easier. So if we solve for y, add and add, we're going to get y equals negative 2x plus 6. Take this and plug it into equation 1. We'll get this plus 2 times y equals 12. And again, we're going to do our y in blue. So then we get negative 2x plus 6. We distribute. We get this minus 4x plus 12 equals 12. These add to 0. If we subtract 12 on both sides, we get this, which is true. This is a true statement, right? This is So because the variables cancel and we finish with a true statement, then they're going to be infinitely many solutions. This is an example of a dependent system. One equation is actually just a multiple of the other, so it's the same equation. One equation is on top of the other. We have infinitely many solutions, and all solutions from this system are going to take on the form x. No matter what x we choose, y is going to take on the form negative 2x plus 6. So we have infinitely many solutions with this being the case. Okay, let's see the time. 2:25. Get out at 3:15. Okay. I think we're okay. Let's keep going. Yeah, we got a little way. Solve the system. Everything canceled. We finished with the true statement, and you see the same result that we got. You see it here. Okay, so next we want to do a demo on the elimination method. So let's give ourselves some space. I added a page, and let me get a copy of this. Again, we're going to do a demo on the elimination method. Nah, I know I did that too high. Let's see, like I said, it doesn't need to be that big. And let's go like this. Paper, let's do some line paper. Okay. So now the goal for the elimination method, we want to get one of the variables to have the exact same numbers but have opposite signs. And so we achieve this result, or we achieve this effect by basically we can multiply any row by any non-zero number and preserve the solution, right? So I think with my other class I did y, so I'm gonna cancel the x this time. If we focus on the x, one of them is 2x, another is 3x. So I'm gonna get both of those to become 6x with opposite signs. I'm gonna multiply the top one by 3. So let me start by getting a copy of the original. We have this 2x plus 3y equals 21. We also have 3x minus 4y equals 23. So I'm going to multiply the top one by 3 and distribute this 3 across all the terms. And I'm going to multiply the bottom one by negative 2 and distribute the negative 2. Okay. So then on top we get 6x plus 9y equals, what is that, 63. On bottom we get negative 6x plus 8y equals 46, negative 46. Now if we add the two equations together, these add to 0. That's going to be 17y equals, if that were 50, that would be 13 plus 4 is 17. So then if we divide both sides by 17, y equals 1, right? So we were able to solve for y. Now let's go back and solve for x. I'm going to choose equation 2 this time. So if we plug this into equation 2, we'll get 3x minus 4 times 1 equals 23. Okay, yeah. So then 3x equals, what is that, 27? Then x equals 9. So our claim is that the solution to the system is going to be 9, 1. Okay. So then we're going to, now we just want to check to make sure that it works. So then we're going to say 2 times 9 plus 3 times 1, right? That's going to be what? 18 plus 3, which is 21, and that's the desired result there. And then the second one's going to be 3 times 9 minus 4 times 1, That's going to be 27 minus 4, which is 23, and that is the desired result there as well. Got a little tongue tied. I was going to say tongue twisted. Peter Piper picked a peck of pickled peppers. Kind of deal. Anyway, let's go paper and get rid of this. Okay. So we confirm that result. Let's go on to the next one. So then we'll have a typed version of what we did. All right. They did it a little bit differently. They just chose a different route, but same result. It's like if we were all going from Morehouse to Stone Mountain. Some people take the top end of the perimeter. Some people take the street. Some people take 20. Some people, I don't know, take different routes, but we had the same destination. That's what we're experiencing here. Okay, let me see the time. Okay, I don't want to keep you more than about 7 or 8 minutes. Okay, yeah, we need to talk about this. We're almost done too. So as soon as we're done, as soon as we finish, I think we can call class. So now with this one, we're gonna. I call this technique U substitution, right? We're going to do the following. No, I don't want that. I guess it's kind of out of the way up there, though. Okay. So we're going to say let U equal 1 over X and let V equal 1 over Y. So then if we make those changes, this equation is going to transform into 2u plus 5v equals negative 5. And we got 3u minus 2v equals a negative 17. Okay. So I think I'm going to use the elimination method. I'm going to eliminate the v. I can just fill the v a little bit better. So I'm going to multiply this top one by 2. I'm going to multiply the bottom one by 5. Okay. So then when we do this, we're going to get 4u plus 10v equals negative 10. We're going to get 15u minus 10v equals, what is that, 15, 35, 85? Negative 85. If we add these two equations together, this adds to 0. That's going to be 19u equals negative 95. Is it 9? 90? No. 5? 50 plus 45? Yeah. Divide both sides by 19, u equals negative 5. I think I need more space. So if u is negative 5, we can solve for v. I'm going to use the first equation. Let me go ahead and add some space. Okay. So then we're going to have 2 times negative 5 plus 5v equals negative 5. It's going to be negative 10 plus 5v equals negative 5. That's going to be 5v equals 5, v equals 1. Right? So if u equals negative 5 and u also equals 1 by x, then that means that 1 by x equals negative 5. If v equals 1 and v equals 1 by y, that means 1 by y equals 1, right? So then with the x term, if we cross multiply and divide, we get x equals a negative 1 by 5. And we also get that y equals 1. So our claim is that the solution to the system is going to be negative 1 by 5, comma 1. Okay. All right. Let me see. Oh, so then we just want to check by plugging in. I feel like this is not going to be too bad to plug in. Let me see. Could just use a calculator. Okay, so the first one, let's do like this. We just want to check. We're going to say 2 divided by negative 1 by 5 plus 5 divided by 1, right? That's going to be equal to what? Negative 10 plus 5, which equals negative 5. And negative 5 is the desired result. And then the second one, we're going to say 3 divided by negative 1 by 5 plus, minus 2 divided by 1. That's going to be negative 15 minus 2, which is negative 17. And negative 17 is the desired result there as well. So then we can stand by this result. Okay. So then let's do the view, single page, like this. Okay. We solved for U and V, and then once we solved for U and V, we went back and plugged them back into those substitutions and solved for the final result. Oh, I think there is one more. Oh, this one isn't too bad. Let me see the time. Yeah, we got time. This is definitely the last one. So we're asked to find the equilibrium point if the supply and demand functions for a brand new DVR are given by the system, where P is going to be the price in dollars and X is the number of units produced and sold. Okay. Equilibrium point is where the supply equals demand, right? So if equation 1 equals P and equation 2 equals P, then we can equate equation 1 to equation 2. So then we can do, let's fix that color. We can do 60 plus 0.0012x can equal 80 minus 0.0008x, right? We're going to isolate our variables, so I add that 0.0008x to both sides. On the left, we're going to get 0.002x. On the right, if we subtract 60 from both sides, we get 20. Divide both sides by 0.002. Why am I not seeing that? Hey Siri, what's 20 divided by 0.002? I got it now.
20 divided by 0.002 is 10,000.
Okay. So this is saying for the equilibrium occurs when we produce and sell 10,000 units. And then we need to see how much do we need to sell them for. So to solve for P, we just plug this into either equation. I'm going to plug it into the second equation. So then P is going to be equal to 80 minus 0.008 times 10,000. You know, kind of ran short on space. So that means move the decimal to the right 4 times. 1, 2, 3, 4. So this is going to be 80 minus 8, which is 72. Right? So then the equilibrium occurs when we produce 10,000 units and sell them for $72 each. Then the supply is going to equal demand. Okay. Style like this. And let me do one other thing. Let's shrink this down. Let me put it here. Okay. So you guys did great. You survived the election, right? I know we're still kind of waiting on the results, and I don't think we're completely out of the woods yet, but, you know, I wouldn't say, well, I can't even be like the worst of it is over, but, you know, we're at least through a checkpoint of whatever kind of calamity might ensue. Yeah, I think that's it for this one. So that actually concludes the last of the new material for this course. So we'll have class on Tuesday. That's going to be a study session, so come with questions. Let me see. Send. I can hang out, so I know that there's a request. I can do like a breakout session, and we can have a private session. But yeah, if there aren't any burning questions, have a great weekend, guys. Just kind of complete all your assignments on Pearson, and I'll see you guys on Tuesday. Enjoy your weekend. Take care.
Thank you.
Let me go ahead and make a copy of this available. this one goes here, here. This one, nope, right there, in the box. Okay. And then let's do a breakout session. We need to go like this, like this, more. We're gonna do a breakout room. Yeah, let's go back over here. So, we just want one room. Hey, you Mr. Sadler, you had a question about something? You should be able to unmute yourself. Let me see. Did you have a question, Mr. Sadler? It looks like you're unmuted now. What kind of device are you on? You can try like quitting and then open it back up, and it might work then. All right, guys. If you didn't have, does anybody have any other questions before I kind of like end the call? Give me just a moment. Kind of like, just give me a moment. Let's do it like this. More? What happened to my more? Hang on. I'll be right back.